When you flick a light switch, you expect electrical energy to be available to run the light that you want to turn on. The question is, where's this electricity coming from? How does it get from the power station to your home? And the other question is, why do they have to transmit it at such high voltages? Sometimes it's as high as 400,000 volts. Why so high when that's so dangerous? Here we can see a diagram of the link between the power station at one end, generating electricity, and your home at the other end. So let's go through the parts. We've got the power station, that is using an energy source to change that energy into electrical energy, and the generator produces the electrical energy at 25,000 volts. We then pass that through a step-up transformer which increases the voltage to, in this case, 132,000 volts, but in some cases it can be even higher, even as high as 400,000 volts in some cases. That's then sent along the overhead cables slung between the pylons until it gets near to your home, when it needs to be passed through another transformer, a step-down transformer this time, which reduces the voltage from 132,000 volts down to just 230 volts. The reason for the step-down transformer is because it would be incredibly dangerous to supply your house with electricity at 132,000 volts. There would be sparks leaping out of the sockets as you went to plug things in, and you would be putting your life at risk every time you went to switch on a light. So we step the electricity voltage down to 230 volts. This is still potentially dangerous and can still kill you, but it's much, much safer than the hundreds of thousands of volts used to transmit electricity across the national grid. So that's the national grid, that's the link between the power station and your home. We've got two transformers, a step-up transformer for increasing the voltage and a step-down transformer for reducing it again. A fact you need to learn is that the electricity supplied to your home is at a voltage of 230 volts. Why such a high voltage? Well, if we just review something that you know about electrical circuits, if we think about a light bulb works because there's a bit of wire in the middle called a filament that glows when it gets hot. And we know that the higher the current, the higher the temperature of the filament, and so the brighter it glows. The same is true about all cables, although not many of them get hot enough to glow, but they do all get hot, and the bigger the current flowing through them, the hotter they get. So, we know that power in an electrical circuit is equal to the current flowing in the circuit multiplied by the voltage. So if we think about the electricity that needs to be supplied to your home to run a 2 kilowatt electric kettle, if the voltage is supplied at 230 volts all the way from the power station to your home, then the current that needs to flow in the cables would be 8.7 amps. On the other hand, if the voltage is increased to 200,000 volts by a step-up transformer for most of the distance between the power station and your home, then only 0.01 amps needs to flow in the cable. Now this means that at the much higher voltage, the much smaller current means that the cable will not get anywhere near as warm as it would do if it was transmitted at 230 volts. And so much less heat energy will be wasted from the cables that are transmitting the electricity. So this is the reason for the very high voltages, to reduce the amount of energy wasted so that the national grid can transmit electricity as efficiently as possible. So that's why we need the transformers, to increase the efficiency of the transmission system, and that happens because we need to get very high voltages so we can have very small currents, and the smaller we get the current flowing in these cables, the less energy they waste as heat.